Functions are an indispensable part of the study of calculus. When you study Calc 1 and 2, you deal primarily with single variable functions. They take a real number as an input, and then they produce a unique real number as an output. Typically, we deal with functions in this explicit form, y equals f of x. Earlier in this course, we introduced a new type of function. We talked about a vector-valued function of a single variable. We take a single real number and we produce a unique output vector. Well, to continue our study in calculus, we need to introduce a new type of function called a scalar function of several variables. You could have a function that has two input variables and one output variable. We would take an element of R2 and produce something that's a real number. We could have a function of three variables. So we take three values as an input and we produce a single number as an output. So we go from R3 into R. Now, generally speaking, we could take any number of inputs. In this case, we'd be taking some element of Rm and then producing a single real number as an output. Now, you could interpret those inputs either as coordinates of a point or elements of a vector. Remember, they're interchangeable in that sense. A function of m variables is a rule that assigns a unique number given by f of x1 through m to each point x1 through m in some set called our domain, and that domain has to live in Rm. Now, in this course, we are going to be focusing on functions of two variables and functions of three variables. It's easy to visualize functions of two variables, and functions of three variables occur a lot in science. So sometimes these things are called scalar fields. Temperature is a scalar function of three variables. You input a location in a room, for example, and then you get back a single number that represents the temperature at that point in the room. Now, to begin with, we're going to talk about inputs and outputs, which means domains and ranges. Now, remember that the domain of a function is the set of all input values that produce a defined output, whereas the range is the set of all outputs. Now, you've had a lot of experience in previous courses finding domains and ranges of single variable functions, and the ideas are very similar when you're working with multivariable functions. So let's say we would like to find the domain of square root x squared plus y squared minus 1 plus the natural log of 4 minus x squared minus y squared. Now, this is a function of two variables because it has two inputs, x and y. Usually the functions that you've been given will have some sort of restriction. So for the square root, the quantity under the root has to be greater than or equal to 0. So that's going to give us that this x squared plus y squared is greater than or equal to 1. You see that when we talk about a two-variable function or a multivariable function, it's a condition on some sort of combination of those letters. For the logarithm, this quantity has to always be positive. And so that ends up giving you that x squared plus y squared has to be less than 4. When you combine these two conditions, you end up getting x squared plus y squared. We need it to be less than 4, strictly less than 4, but greater than or equal to 1. So the domain in proper notation is going to be the set of all points x and y. When we put this vertical bar, it means such that, and then we state the condition. X squared plus y squared is less than 4. Now, it's going to be the case that when we have a two-variable function, we can visualize the domain using x and y coordinates or just some two-dimensional coordinates. We've naturally got this condition x squared plus y squared. We've got the equation of a circle between radius 1 and radius 2, where we are allowed to be at 1. We are not allowed to be equal to this value of 2, and we can be any value in between. Shade in all of these values here to show that they're allowable. Now remember that when you've got a dotted line like this, you have to exclude the points. How do we visualize functions of multiple variables? And we're going to talk about the graphs of two variable functions to begin with, z of f of x and y. And when we talk about two variable functions, what's important here is that we understand how the domain is visualized. The domain we are going to put in the xy plane for each point in the domain. So each xy produces an output, and that output uses those two numbers. So all of the output values are going to live on the z-axis. We need two input axes and one to talk about the output. This is going to generate some dot, and that single dot represents the height of the function. Every single input would create a single output. Remember, it's a function. What we would find is that we would generate a graph of our function. The set of all heights is the graph of this function f. Now, generally speaking, the graph of a function will be a surface in R3. The graph of some function f of x and y has to pass the vertical line test. If it doesn't pass the vertical line test, it can't be considered a function. We've seen lots of different functions of two variables already. So we talked about paraboloid. Now, paraboloid is an upside down bowl shape. And remember, it's just a shell. Take a vertical line. This vertical line would intersect just once. So here it would pass the vertical line test. If we were to take a different sort of surface, like an ellipsoid, and if we were to take the vertical line test, you could see that we run into trouble because this vertical line would touch twice. So an ellipsoid does not represent the graph of a function. If we can solve an equation with three variables, x, y, z, for the z, and get an explicit formula with a unique output, then we will have a function, z equals f of x and y. Otherwise, if we can't do it, we're going to get an implicit equation with three variables. So it would generally be written as some f of x, y, and z equals 0. Now again, the equation of our parabola here fits this form, but the equation of a sphere runs into problems. We've talked about x squared plus y squared plus z squared is equal to 1. Right now, this is written in implicit form. So there would be our capital F. I could solve this equation for z squared. I'd get 1 minus x squared minus y squared. If I take the square root of both sides, here's where I run into the uniqueness problem. Remember that the square root of z squared is going to give me an absolute value. And now I have two possibilities for outputs. I can either have the positive output. So if z is positive, what this is going to do is produce the top half of the sphere. But if z is negative, this is going to produce the bottom half of the sphere. So if we want to graph functions of two variables like this, we see that we need 3D coordinates to do it. Now, the best option if we want to get a picture is to use computer software to visualize everything. If we're restricting ourselves to doing it by hand, we've already seen quadric surfaces. We've also seen cylinders. Now, this gives us some basic examples with which to graph things, but there are other ideas and there are other techniques when you don't have one of these surfaces. And we're going to talk about something called level curves and contour maps. So it comes back to, again, this idea of visualizing things in 3 dimensions. Now, as discussed, a function of two variables needs 3 spatial dimensions to visualize it. A level curve is when you intersect your function with some plane, z equals k. So what we're going to do is take a plane at some height, z equals k, and then intersect it with the surface. It's going to create a curve. Now that curve is going to project to the xy plane. It's going to produce what's called the level curve for z is equal to k. or in other words, when f of x and y is equal to k. Now, if this is intersecting at some value k1, this will be the k1 level curve. If I take a different plane and intersect it at a different value, then it's going to produce a different level curve. So this would be the level curve that occurs when it's at the height k2. And then what we will get would be another curve down here. So this would be the k2. And as I keep intersecting with different values of k, I'm going to produce different curves down here, and we like to label them. The picture that we get is what's called a contour map. A contour map is a 2D picture that contains all of the level curves. You've typically seen this as what's called a topographical map in geology. This is where they like to use a 2D picture to try to show you different heights. The value that you see for each one of those level curves indicates how high the mountain or valley is. Now, I want to give you an example of this. So let's talk about the function f of x and y is y over x squared plus y squared. I want to talk about level curves. This function is equal to k, some constant. So in my particular case, I'll have y squared over x squared plus y squared as a constant. I can reorganize this to get x squared plus y squared by itself on this side is y over k. If I reorganize that further, here's what I will end up with. Now in this case, to make some progress, I need to complete the square. You can review this technique on your own. The magic number that I have to add in is half of the coefficient of this single y term. So that would be negative 1 over 2k, and then I need to square it. So it'll get 1 over 4k squared, and whatever I put into the equation, I have to take out. Now, the purpose of doing this is that I'll get these three terms, and these three terms end up making a perfect square. The perfect square here is y minus 1 over 2k all squared. And this is 1 over 2k squared. Now, because I divided by k at some point, k is never allowed to be 0. This represents circles. The center of these circles is going to live 0 and 1 over 2k, and then the radius of these circles is always the absolute value of 1 over 2k. Now, the circles here are all on the y-axis. And if I choose different values of k, I will get different level curves. So for example, if k is equal to 1, I will have a circle with a center 0, 1/2 and a radius of 1/2. So if there's a half and there's a 1, there's a half and a negative 1. What ends up happening is that I will have a circle. Its radius will exactly touch right at the origin. This is the k equals 1 curve. Well, if I did the same thing for k equals negative 1, I would get almost identical results, except that the center would now be below. K is equal to a half. My center will be 0 and 1. My radius will be 1. So that means I'll have a bigger circle. It has its center here at 1, but it has a radius of 1. So now I'll have a larger circle that touches at the origin. If I were to do the same thing for negative 1/2, I would have this as my result, and it would be a similar picture. I'd have a larger circle. K is equal to 2. I'd be at 0 1/4 with the radius of a half. So I'd have a smaller circle inside there. And the same thing would happen if I were to pick k as negative 2. I'd have a smaller circle in there. So this is a contour map of this particular function. What does this show me in terms of the graph of f? The purpose of level curves is to help you go from a 2-dimensional picture up to a 3-dimensional picture. And you can see here that all the blue curves correspond to z values that are positive. So these are above the xy plane, whereas all the green curves are z values that are negative, below the xy plane. So if I take a look at a 3-dimensional picture, I can get higher and higher values of z, but you see that the circles become smaller and smaller in radius. Same thing happens for the negative values of z, but they drop down, they go negative. So the graph of f has to look something like this. There'll be a z-axis that comes up this way, and I'll have some sort of almost mountain type shape. And then if I go ahead and I plot this, I'll have the blue level curves that go up. But if I were to go and visualize it down on the other half here, I have these negative values that drop down like this. And all of these negative level curves live down here. And you see, this is the point of these contour maps. You're trying to assemble some sort of understanding of this function based on just some 2D information. Now, finally, we can't graph a function of 3 variables. It's not possible. Why? We need 3 coordinates for the domain, the inputs, but we need 1 additional coordinate, spatial coordinate, for the output. And that means we need 4D coordinates. Humans can't see in 4 spatial dimensions. It's unfortunate, but we are stuck.